In this video, we're going to look at the rules of indices. Let's start by considering a number raised to a power. So we might have 3 and we raise this to the 4th power, or 3 to the power 4. We call 3 the base, so this is a base. And then the number 4 we could call a power, so this could be a power. We could call this now an index, or we could call this an exponent. So just writing those down, we've got now on here either a power, an index, or an exponent. In this video, we're going to look at the rules of indices. As you can see, that comes from the idea just here of the index. In the first video, we're going to lay down some of the rules, and then in a later video, we will look at some harder examples. So let's start off. What I've done here is put a list of the rules of indices. I've called them 1, 2, 3, 4, 5, and 6. If you pick up a textbook, it won't say the rules of indices, number 1 is this one. It's no particular order, I've just defined them in this order. So let's go ahead and start with the first rule. If we're multiplying and we have like bases, so in this case A, and all we've got now is a power of m and a power of n, we add. So when we're multiplying like bases, we add the powers. We can see this numerically. So if I had now 2 to the power of 3 multiplied by 2 to the power of 2, we know that 2 to the power of 3 is going to give me 8, 2 to the power of 2 is going to give me 4, and that's going to give me now 8 times by 4, which is 32. Now 32 is 2 to the power of 5. So 2 times by 2 times by 2 times by 2 times by 2. And we can see that I could have just added these two powers together. So in general, if we have the same base and we're multiplying, we add the powers. Let's look at an example of that. Let's say we had a to the power of 3 multiplied by a to the power of 4. Then all we've got now is 3 plus 4, so it's the same base, and it would be a to the power of 7. A common error students make is if we have, for example, a multiplied by a to the power of 4, they write down that this is a to the power of 4. We need to get into the habit of writing that this is going to be 1. To begin with anyway. Once you're happy with that, it should be fairly straightforward. So 1 plus 4 is going to give me 5, and that's going to give me a to the power of 5. Sometimes we might have a numeric value, so we might have 2a to the power of 3 multiplied by 4a to the power of 6. All we do is multiply the numeric values, so we've got 2 times by 4, which is going to give me 8, and then we consider a. So we've got the same base and we add the exponents, so we'll get a to the power of 9. Often they won't be as easy, so for example we might have 3a to the power of 4 multiplied by 2/3, and we might have a to the power of -2. So if we multiply the numbers, 3 multiplied by 2/3, well that's just going to give me 2 with the 3's cancelling. And now I'm doing 4 plus -2, so we're going to have a to the power of 2. Just be careful, if we've got a negative here, you're adding these, so essentially you're subtracting the 2 away. Sometimes we might not get now integer values on our powers, so we might have, for example, 4a to the power of 1/3 multiplied by, let's say, 5a to the power of 1/2. So we multiply the two numbers, 4 times by 5, that will give me 20, and now we need to add 1/3 and 1/2. So 1/3 plus 1/2 is going to give me 5/6. So we'll have a to the power of 5/6. Later on in the video, we will look at some fractional indices or fractional index and then work through some problems with those. But being able to add, subtract, multiply and divide fractions is absolutely crucial throughout your study, certainly at this level anyway. Okay, let's move on to the second rule. So with the second rule, very similar. We've got a to the power of m divided by a to the power of n. This time we're subtracting now the powers. So if we're dividing like bases, so when I say like base, it might be 2, it might be 5, it might be x. These are like bases. So let's go ahead and do the examples of these. So let's look at now a numeric example. So let's say we've got 3 to the power of 3 divided now by 3. Okay, so let's first write this as 3 to the power of 1. Now 3 to the power of 3 is going to give me 27. Divided by 3 is going to give me 9. If we look at 9, 9 is 3 to the power of 2. And we can see from here, all we've done is subtracted the powers. An alternative way to look at this would be as a fraction. So what we have is 3 to the power of 3 divided by 3 to the power of 1. And we could write this out. So it'd be 3 times by 3 times by 3 over now 3. We can see these are going to cancel, and this would just give us 9 or 3 to the power of 2. Clearly though, if I had now, for example, 3 to the power of 4,080, let's write this for 4,891 divided by, and let's say we've got 3 to the power of 674, we wouldn't want to write this out all of those times and cancel off. We would simply subtract away. So let's look at an example of that. Let's say we've got now a to the power of, let's say 4, and we've got now divided by a to the power of 3. So all we're going to do is subtract the powers, so it'll be a to the power of 1, or we could just write a. If we had now a to the power of 5 divided by a to the power of minus 1, this is going to be 5 subtract minus 1, so that's going to give us now a to the power of 6. So 5 minus minus 1, we're going to add them. Again, we might have some numeric values here. We might have, let's say we've got 8a to the power of 3 divided by 4a to the power, and let's have on here, let's go for minus 6. So we're going to first divide the numbers. In the last example, we looked at multiplying the numbers. So in this case, 8 divided by 4 is going to give us 2. Then we're going to have a cubed, or a to the power of 3. So we've got a to the power minus 6, so that's 3 minus minus 6, which is going to give me now a to the power of 9. So simplifying, that's what we end up with. We might see this in terms of a fraction. So let's look at this as a fraction. Let's just get some space here. Let's say we had now, let's say we had 15 and we had a to the power of 4. And then in the denominator we had 3 and then we had a. So 15 over the 3 is going to give me 5. We've got a to the power of 4 divided by a to the power 1. So we subtract the powers and this will give me a to the power of 3. So just putting a little 1 there, 4 minus 1 is going to give us 3. So nice and straightforward. And that's another way of looking at it. So if we, for example, have, let's do something else. Let's say we've got 8 and then we'll have a to the power of minus 3 divided by, and we'll write down 1/2. Let's go for a to the power of 4. We're going to do 8 divided by 1/2. If we think about 8 divided by 1/2, 8 divided by 1/2 is the same as 8 multiplied by 2. All we do is invert the fraction and multiply. So we're going to have 16. We've got now a to the power of minus 3. So we need minus 3 and we need to subtract away 4. So we're going to have a to the power of minus 7. Later on we'll see how this can be written as 16 over a to the power of 7. And that's one of the rules that we'll look at, and that one is just here. But for now we could write it like so. Okay, let's look at another example. Let's say we had a to the power of m plus n divided by a to the power of m. And we were asked to simplify this. So let's rewrite this. Let's see what we can do. This goes back to the first rule. The first rule is if we're multiplying the same basis, we add them. So I could actually write this as a to the power of m multiplied by a to the power of n, and then what we'd have in the denominator now is a to the power of m. We can see that these are going to cancel and we're left with a to the power of n. Alternatively, you could just look at this as an equation, m plus n, or I say, well, writing it as an equation, just writing it as an expression, minus m. And we can see that that's just going to give us now n. So we'd have now a to the power of n. So all we've done is looked at rules of indices. What this is, and I'll just write it here, let's write it here, a to the power of m plus n divided by a to the power of m. So it's m plus n minus m, which is just going to give us the n. So do be aware of different ways that those can be written. So that gives us now an example of the second of these rules. Let's look at a slightly harder example. Let's say we've got now, and we'll write one down here, let's do something slightly more tricky. Let's say we've got 2a to the power of 1/3 divided now by 4a to the power of 1/2. So we've got 2 divided by 4, which is going to give us 1/2. In this kind of work, especially as a non-calculator, it's always better to work with fractions. A fraction is at least as accurate as a decimal. I really don't like seeing 0.5 written there, because sometimes, for example, we can't express a decimal in what I call exact form. So just do write these as fractions. So what we have now is 1/3 minus now 1/2. So all we're going to have then is a to the power of minus 1/6. So all I've done is subtracted 1/2 from 1/3, and we could write that like so. So that's the second rule that we've got here, and that is when we have the same base or like bases and we're dividing, we subtract the powers. Okay, let's move on to the next one. The third one, a to the power of m raised to the power of n, is a to the power of mn. So if we raise a power to a power, then we go ahead and multiply these two numbers. So let's look at an example of that. Let's say we've got 2 to the power of 2, and we raise this now to the power of 3. So if I consider what this is going to be, this is going to be now 4. 2 squared is 4, 4 to the power of 3, and that's going to now give us 64. Now 4 to the power of 3 is 64. If I just multiply these, we would have had 2 to the power of 6. 2 to the power of 6 is 64. Often students add these. We're not doing that, we're multiplying. So if we're raising a power to a power, we multiply. So this wouldn't now be 2 to the power of 5. It would be 2 to the power of 6. It wouldn't be 4 to the power of 6. As we can see, it's now 4 to the power of 3. So let's look at an example of that. Let's say we've got a to the power of 4 raised now to the power of 5. This is going to give us now 4 times by 5. So we've got a to the power of 20. If we have a numeric value in here, we need to be very careful. So let's say we had 2a to the power of 4 raised to the power of 5. A killer mistake now is pupils write 2a to the 20th, or they write 10a to the 20th, which is even more frustrating. What I suggest you do to begin with is put the little power of 1. All we're doing is multiplying the indices. So it'll be 5 times by 1 and 5 times by 4. So we're going to get 2 to the power of 5 multiplied by a to the power of 20. So 2 to the power of 5, that's going to give me now 32. So we get 32a to the 20th, or a to the power of 20. This would be different now if we had 2 and then a to the power of 4 raised to the power of 5. This would be 2 lots of a to the power of 20. Just be careful with that. It's a common error students seem to make quite frequently. So let's look at some examples of that. Let's say we've got now 4, and then let's say we've got p to the power of minus 2, and we raise this to the power of 3. This is going to give me 4 to the power of 3, and then we're going to have p to the power of minus 6. 3 times by minus 2 is minus 6, so 4 to the power of 3 is 64, p to the power of minus 6. And later on we can see that that could be written as 64 over p to the power of 6. If we have a to the power of minus 3 raised to the power of minus 2, we're going to multiply minus 3 and minus 2. So this is going to give us now a to the power of 6. Minus 3 times minus 2, we're going to end up now with this value like so. So that's a nice example. Let's go for another one. Let's say we got 2a to the power of 3x, and then we have b to the power of x, and we'll raise this now to the power of 4. So I'm going to end up now just writing myself a little 1, just so I don't for some reason put 2 or put 8. I'm going to have 2 to the power 4, which will give me 16. I'm going to have a to the power of 12x, 4 times by 3x, so we're going to get 12x. And then finally we're going to get b to the power of 4x. So if I wanted, I could write this now as 16 a to the power of 12x, b to the power of 4x. So we're just using the rules of indices now to make this easier. Let's look at one of the properties of this, and I'm just going to write this down here. A to the power of m raised to the power of n is the same as a to the power of n raised to the power of m. We say multiplication is commutative, and if we just look at a numeric example of this, let's say we've got 2 to the power of 2 raised to the power of 3. Well, this is going to give us 2 to the power of 6 in the same way as if we had 2 to the power of 3 raised to the power of 2. So if we look at it now, I'm just putting the numeric values in, 4 to the power of 3 is going to be the same now as 8 to the power of 2, and they're both equal to 64. So this is a property that you can really use and manipulate to help you out when you're dealing with the rules of indices. So for example now, if you had a to the power of x raised to the power of 2, we could write this now as a squared to the power of x, or vice versa. And often you'll see that this will get you out of trouble when you're looking at certain equations. Okay, let's look at another particular feature of this rule. Let's say we've got now a to the power of m. So we've got now a to the power of m, and in fact we'll just write it like so. Let's write it just here. Let's say we've got now this value here. So let's, and this is just strained slightly away. Now, if a is negative, let's write this here. Okay, so if a is negative, when we have odd and even powers, this will dictate what answer we got. So if a is negative and m is odd, so let's write this down, we're going to get now a negative answer. So let's look at that. If I've got now minus 2 to the power of 3, then what I'm going to get now in this particular case now is minus 2 cubed, which is going to give me minus 8. So if we take now a is negative and we've got an odd power here, we're going to get a negative answer. If we write now if a is negative, so let's write this down, and m is even, so let's write that here, we're going to end up with a positive value. So again, let's look at this. If we've got minus 2 to the power of 4, or 2 is probably easier, but we'll look at 4, this is going to give us positive 16. So let's write that there. This is simply saying that this is minus 2 multiplied by minus 2 multiplied by minus 2. So that will give us now a positive, and we're going to end up now with a negative. So that's something else to think about when you're evaluating. So if we've got now a, where a is a negative number, and m is odd, we end up now with negative value. If a is negative and m is even, we end up with a positive value. So that's just something to consider if you're evaluating. So if you're given particular values for a and m, just to be aware of, especially later in your studies. For example, when you're looking at something called the binomial expansion, often errors are made as a result of not appreciating which terms are going to be odd and which are going to be even, giving us negative or positive values. Okay, let's now move on to the next rule. So we've got a to the power of 0 is equal to 1. Now this is when a itself is not equal to 0. So if we had now a is minus 1, a is 10, a is x, that's fine as long as that value is not 0. So I can write down that a to the power of 0 is equal to 1, and that is when a is not going to be equal to 0. And if you're unfamiliar, haven't met this sign before, this is just telling me that it's not equal to. So why is this the case? Well, let's start with some numeric examples. Let's start with 2 to the power of 6. 2 to the power of 6 is 64. 2 to the power of 5 is going to give us 32. 2 to the power of 4 is going to give us 16. 2 to the power of 3 is going to give us 8. 2 to the power of 2 is going to give us 4. 2 to the power of 1, or just 2, is going to give us now 2. Now, what are we doing here? If we look, we're decreasing the power by 1 each time, and this side is dividing by the value of 2. So what I'm doing is dividing by 2. So divide by 2, divide by 2, and then this side I'm simply subtracting 1 each time. So if we subtract 1 from here, we're going to get 2 to the power 0, and we need to divide this number by 2, which is going to give us 1. Now, you can see that's going to hold for all of these values right here. So all we're going to do is end up now coming down here, and we're going to have now anything to the power of 0, as long as it's not 0 itself, is going to give us 1. So let's look at that in action. If we had now 2a and we raise this to the power of 0, that's going to now be 1. We've got 2 to the power 1 and we've got a to the power 1, and we just multiply them and we end up with 1. So whatever is in that bracket is going to end up giving me 1. So if we looked at a simple example, if we had now x, some value of x, x to the power 0, that's going to be 1. If we had 6 to the power 0, that's going to be 1. If we had now 2 and then a plus b raised to the power 0, then the bracket here will give me 1. 2 times by 1 will give me 2. If we had, for example, x and then we had, let's say, x plus y raised to the power 0, that's just going to give me x multiplied by 1, which will end up now with x. So a nice straightforward rule, and it's something that you just have to be careful with in terms of making sure that you evaluate it correctly. So this is the 0 power. So if we raise a base, the base is a to the power 0, where a is not 0, we end up with 1. So that's now the 4th rule. What we're going to do now is move on to the next one, and this I've called the 5th rule. This is now a negative power, so we're raising our base to a negative power. What I'm going to do is extend my table, and I'm just going to start off. Let's just say we start with 2 to the power 4. 2 to the power 4 is 16. We've got now 2 to the power 3, which is going to be 8. We've got 2 to the power 2, or 2 squared, which is 4. 2 to the power 1, or just 2, that's going to give us 2. We see now 2 to the power 0 is going to give us 1. It follows that if I now subtract another 1 from the left-hand side, 2 to the power of minus 1 means that we're going to need to divide this side by 2 again. So I can write this now as 1 over 2, or if I like, 1 over 2 to the power 1. If I subtract another 1, I'm going to get 1 over, and I need to divide this by 2, 1 over 4, or we could write this now as 1 over 2 squared. If I look at the next one, 2 to the minus 3, we're going to get 1 over 8 as we divide it by 2, or we could say 1 over 2 cubed. And we could go right way, dot, 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 and so on and so forth. So let's just dot, dot, dot. And we've got 2 to the power of minus m will be equal to 1 over 2 to the power of positive m. So this now is the 5th rule. If we have a negative power, we can simply write it as 1 over the positive power. So let's look at some examples. Let's say we've got a to the power of minus 6, then this is going to be 1 over a to the power of 6. If we have 2a to the power of minus 6, this is going to be 2 over a to the power of 6. Often students write this as the 2 in the denominator. What we're looking at now is 2 lots of that value. Now, if I had 2a and we raise this to the power of minus 6, then this would be 2 in the denominator this time. So we've got a little 1 there, so it would be now 2 to the power 6, and then we'd have a to the power 6. So we could write this now as 1 over 64 a to the power of 6. So do be careful. Check that you have in your denominator or numerator the correct value. These two things are not the same. Okay, let's look at another example. Let's say we had, and let's write something slightly different. Let's say we've got a to the power of minus m, and we raise this now to the power of minus n. Now straight off you're thinking, well, I can write that as 1 over now a to the minus m. But let's go back to our rule back here, and all we've got then is minus m times minus n, which will give us a mn. So we're multiplying. So just be a little careful when you're doing those examples. That's just a little quirk, or me going back to the one before. Okay, let's look at another example of this. Let's say we've got now a, and we'll take this a over b. So we've got two values, a and b, and I'm going to raise this, and we can't have b to be equal to 0. Let's go ahead and write a over b, and we're going to raise this to the power of minus m. A result of this is that we have b over a to the power of positive m. So if we have a negative index or negative power, and we can simply invert that fraction and write it to the positive power. If you consider what I've done here, I've got now a to the power of minus m, which is the same as 1 over a to the power of m, and I've divided that by b to the power of minus m, which is 1 over b to the power of m. If I look at this, what I've got here, and I'll write it just here, let's just write this out, we've got 1 over a to the m divided by 1 over b to the power of m. If we're dividing, we could write this as a, so 1 over a to the m multiplied by now the inverted fraction right here, which would be b to the m over 1, and we can see that this gives us now b, and we'll write this out, b to the m over a to the m, which of course we could write now as b over a to the power of m. These things are identical. So going back to this, if you have a negative power, you can invert the fraction and then simply write it to the positive power. So I'll just go through that. Let's look at an example of that. Let's say we've got, and I think in fact we'll look at this a bit more when we come on to the next one. But for example now, if I had, let's say I've got 5 over 3 and I raise this to the power of minus 2. This is the same as doing 3 over 5 to the power of positive 2. So if we consider now 3 to the power of 2, that's going to give me 9, and 5 to the power of 2 is going to give me 25. Often checking these on a calculator is quite handy, but certainly don't rely on the calculator, as in some exams you won't get them. So that now is the negative power. A to the power of minus m is 1 over a to the power of m. In the next video, we'll spend some time working through examples of this. The whole idea of this video is to give you the foundations, and then we'll look at some more challenging examples. Okay, let's move on to this one. A to the power of m over n is equal to, now we've got two ways this can be written. We've got the nth root, so when we've seen a square root before, we just see a square and just have the root here. We don't have the 2 here. But if we have the cube root, we'd have 3. And then we have to the power of m. I don't like this notation. I find it really quite challenging. What I like to do is think about the nth root, and then we raise to the power of m. So if we have a fractional index, we take the nth root and raise it to the power of m. So let's look at a numeric example of that, and we'll start with something nice and straightforward. Let's say we've got 36 to the power of 1/2. We need to take the second root. The second root is the same as the square root, and then raise it to the power of 1. Now I would like to see this initially written like so, and this seems a little strange, but hopefully you'll get used to it. So the square root of 36 is going to give me 6, and then I raise this to the power of 1. So we end up now with 6. So all I've done is just taken the second root. It's not dividing it by 2. Again, that's a massive pet hate. You're taking the second root. So what times by what is going to give us 36, and then we raise it to the power of 1. Now, why is that important? Let's look at doing 36 to the power of 3 over 2. So what I'm going to do is write 36 to the power of 1/2 raised to the power of 3. So I'm taking the square root and then I'm cubing it. And that goes back to this definition right here. So all I'm doing is using this one right here. So what we end up with is 6, and then we raise that to the third power. So 6 times by 6 times by 6 is going to give me 6 cubed, which is 216. So we've taken the second root and raised it now to the third power. So if you like that notation, ideally get comfortable with it, as it may ask you in a particular question to write the different forms. And in the next video, we will look at some examples of that. Now, another thing to appreciate with this is when you're looking at surds, if we have the root of a, this now is the same as a to the half power. So just be aware, especially when you come on to topics like differentiation and integration, you might see an expression written as 2 root a, and we'd write this now as 2a to the 1/2 power. So let's work through some basic examples of this before we move on. So let's say now we'll have some numeric examples. Let's say we've got, and we'll say, let's go for 25, and we will have this now to the power of 3/2. So what we'll have then is 25, we will raise this to the half power, which is the square root, and then we will cube that. Square root of 25 is 5, and then we raise this to the 3rd power, which will give us 5 cubed, which is 125. Let's look at some other examples, and we can take, let's go for something else. Let's say we've got now 8 to the power of 2/3. So let's go ahead and look at this. So what we've got is 8 to the 1/3 power. So we're taking the cube root and then we're squaring it. The cube root of 8 is 2, and we raise this to the power of 2, which is going to give me 4. And if you were asked to evaluate that in an exam for 2 marks, you need to show how you're doing this. I like to do it just here, just to ensure that we're not making errors. Let's now look at some other examples. So far, we've seen these are positive fractions. We won't always have a positive fraction. So let's take that example last time. Let's say we've got this time 8 to the power of -1/3. So what we could write then, and I'll do this step by step, is 8/1 to the power of -1/3. We've seen if we get now a negative index here, we can invert the fraction, so I can write it as 1/8, and raise this to the power of 1/3. So all we're going to have then is 1 over the cube root of 8, which is going to give us 1/2. So that's a nice example of that. If we had something slightly harder, let's say we've got 25/64 to the power now of minus, let's go for 3/2. Let's make this slightly more challenging. So we could invert the fraction, 64/25. We could raise this to the positive 3/2. So what we would do is take the square root and then cube it. Now, of course, you could write this as 64 to the 1/2 over 25 to the 1/2 and raise it to a 3rd power, or you could write this like so. So we're going to have this to the power of 1/2, and then we're going to cube it. So if we think about now 64 to the power of 1/2, the square root of 64 is 8, the square root of 25 is 5, and then we raise this now to the 3rd power. So we got 8 cubed, which is 8 times by 8 times by 8, which is going to give me 512. And then we got 5 times by 5 times by 5, which will be 125. So 8 cubed, if you like, you could write that as 2 cubed, and then to the power of 3, 2 to the power of 9 is 512 as well. Just be aware that, again, and this is just sort of moving back a couple of things, we could write now, and this is quite a nice thing to look at, we could write this now as 2 to the power of 3 over 5 raised to the power of 3, so we get 2 to the power of 9 over 5 to the power of 3. I'm just looking at different ways, and do be aware that that's something that you could see. Okay, let's look at a couple more. Let's say we had now something a bit nastier. Let's say we got 0.16. Let's say we were given 0.16 raised to the 0.5 power. The first thing I want to do is turn this into fractions. So what I've got then is 16/100ths. So I've got 16/100ths raised to the power of 0.5, which is 1/2. I'm now going to look to simplify that. I can divide the numerator and the denominator by 4. So that's going to give me 4/25 to the power of 1/2. Square root of 4 is 2. Square root of 25 is going to give us 5. So 2/5, or we could say 0.4 if they asked for a decimal answer. Now, does that work? Well, it's asking me essentially what the square root of 0.16 is. Now, 0.4 times by 0.4 is equal to 0.16. So we can see that our rules of indices have held up just there. And again, you could say, well, I kind of know what I'm doing on that first one. I'll write it out like so. But if the numbers aren't as nice, or you're dealing with algebraic terms, then you just have to be slightly more on your guard, as it were. Okay, let's look at some more examples. Let's say we got p to the power of 2 over q to the power of 4, and we raise this now to the power of minus 1/2. So let's rewrite this. Let's write this as q to the power of 4, so I'm simply inverting the fraction, over p squared, and we're going to raise this to the positive 1/2. So all we're doing is using our rule. So if we think about it now, this goes back to the rule here. So I've got now q, and I'll write this here, we're going to multiply these two. So we're going to get q squared, and then we're going to multiply the 2.5, which is going to give me 1, so we'd have q squared over p. That's just going back and we're combining the rules just here. In the next video, we will look to combine more rules. But for now, hopefully you can see how that works by using the third rule here with the sixth one. We could look at something slightly harder. Let's look at, let's say we've got 4p, and we might put this over, let's say q squared, and we'll raise this to the power of 1 and 1/2. The first thing I'm going to do is write a top-heavy fraction. So I'm going to write this as 4p over q squared to the power of 3 over 2. So let's see what we've got here. We're going to have in the numerator 4 to the power of 3 over 2, p to the power of 3 over 2. Just consider that this is just a 1 and this is just a 1. So we're going back to using this rule right here. Then we're going to multiply 3 over 2 by 2, which is going to give me just now the 3. The 2's are going to cancel just here, so we end up now with q to the power of 3. If we consider 4 to the power of 3 over 2, we take the square root, which is 2, and then cube it. So that will give me 8 p to the power of 3 over 2 divided by q to the power of 3. So that would be my final answer, and that's a slightly harder example. So all we've done is look to employing that rule. And as stated, in later videos, we will come on to looking at examples of how that can be used. We're going to end up, or end the video at least, looking at some equations. Now, sometimes these will come up, sometimes they won't, but it's important to appreciate them and be able to work with them. So let's say we've got an equation and we're asked to solve now. Let's say we wanted to solve for x. And we had now x to the power of, and we'll have, let's say, to the power of 2 over 3. And that's going to be equal to, let's go for now 1 over 100. So let's see what we can do with this. What I want to do at this stage, again, there are lots of different approaches to this. I want to now get x. So if I've got x to the power of 2 over 3, what I want is 1. So I'm going to write this now as x to the power of 2 over 3, and I'm going to raise this now to the power of minus 3 over 2. If I'm going to do that, I need to do that to both sides of the equation. So all I'm going to do is write this over here, and we're going to have a minus 3 over 2. I could have inverted this to begin with and inverted both sides, which of course could make it easier, but it's entirely up to you. So I could have written that now as a to the positive 2 over 3 is equal to 100. What I'm looking to do now is use this rule of indices, or this particular a to the m raised to the n is the multiple. As if I multiply these two, I'm just going to get x to the power of 1, or x. This now, and I'm going to invert this, is going to be 100 to the power of 3 over 2. So what we end up with is x. If we take the square root of 100, we get 10, and we cube that, we're going to get 1000. So that's what we end up with using rules of indices. So in this particular case, I could have just written now x to the power of positive 2 over 3 will be equal now to 100 over 1 by inverting the fractions. So I could have written x to the power of 2 over 3 raised to the power of 3 over 2 will be equal to 100 to the power of 3 over 2. So we can see that x to the power of 1 is going to be 1000. So if you're not confident we're working with the negatives, there is an option for you. So you can invert that fraction straight away. Okay, let's look at another example. Let's say, and we'll write one out, let's go for 2 to the power, or let's have 2x to the power of 1 over 4 is equal to 64 over x. Now, be wary that you might see this as x to the minus 1. The first thing I'm going to do is divide both sides of the equation, and I'll do this step by step, by 2. So I've got x to the power of 1/4 will be equal to 32 over x. At this stage, I'm going to multiply both sides of the equation by x. So I get x to the power of 1/4 multiplied now by x to the power of 1 will be equal to 32. I'm going to use the rules of indices. 1/4 plus 1. We're going back now to the first rule. So I'm multiplying like bases. 1/4 plus 1 is going to give us 1 and 1/4, or as a top heavy fraction, 5 over 4. And that's going to give us 32. Now, if we raise both sides to the reciprocal, so we've got x to the power of 5 over 4 raised to the power of 4 over 5, that's going to give us 1, and we can say that's going to be equal to 32 to the power of 4 over 5. So we've got x is equal to, these are just going to cancel each other out, 32 now, and I'm going to write this out, to the power of 1/5 raised to the power of 4. So if we look at this, we've got now 32 to the 1/5, so the fifth root of 32, so we've got x will be equal to 2, and then we raise this to the power 4, and we can see that x is 16. At this stage, I want to check if this works. So I've got now, and we'll sub it in, so we've got two lots of 16 to the power of 1/4. Is that equal now to 64 over 16? So let's look at this. This 16 to the 1/4 power, the quarter root of 16 is 4. Sorry, there's my error. 2, it's 2. Two lots of 2 is going to be equal to 4, so we can see that holds. I've just done my pet hate. My pet hate is for some reason dividing by it. So I'll hold my hands up on that one. The fourth root of 16, don't divide it by 4, just take the fourth root. So we can see that holds true. And I've really done that step by step, but hopefully that gives you some idea how you could deal with an equation using the rules of indices. Let's look at another example. Let's say, and I'll just move on, let's say we've got 5, and we've got 5 to the power of 6x minus 1. And we'll put this equal now to 25. Now, this looks a bit daunting, but let's rewrite this now as a power of 5. So we've got now 5 to the power of 6x minus 1 would be equal now to 5 squared. So we can see that the bases are the same. 25 is 5 squared. If the bases are the same, the exponents are the same. So we've got 6x minus 1 will be equal to 2. 6x will be equal to, adding 1 to both sides, 3. And then we can see that x dividing both sides by 6 would be 1/2. So does that work? Well, let's put that in. We've got 5 to the power of 3 lots now of 1/2, sorry, 6 lots of 1/2, which is going to give us 3 minus 1. Does that equal 25? Well, 3 minus 1 is 2, 5 squared is 25. So we can see that that works right there. So that's a nice example of a particular equation. Another one, we might have 2 to the power of x squared plus x is equal to 64. So with these non-calculator questions, what we're looking at doing is rewriting this as a power of 2. So I've got 2 to the power of x squared plus x will be equal now to 2 to the power of 6. 64 is 2 to the power of 6. Therefore, if the bases are the same, the exponents are the same. So x squared plus x would be equal to 6. We have the quadratic equation in x, so we've got x squared plus x minus 6 is equal to 0. So I'm writing that now in the form ax squared plus bx plus c is equal to 0. That looks like it's going to factor, so we've got x plus 3 multiplied now by x minus 2. That will be equal to 0, so we can see that x would be equal to minus 3 or x would be equal to 2. We need to just check these, check that they work. So let's go ahead and do that. Let's start now with the minus 3. So I'm going to have 2 to the power of x squared. If I square this, I'm going to get positive 9. And we put that in. So is this going to be right? So let's go ahead and put that in. So can we use the minus 3? I put it in, I square that, that's going to give me 9. And then I add to it x, which is going to give me now minus 3. Does that equal 64? Well, that gives me 2 to the power 6, which is 64. So we can see that that holds. Let's now put in the 2. So we got 2 to the power of 2 squared, which is 4, plus now the 2, which is going to give me 64. So again, 2 to the power 6 is equal to 64. So we can see that that holds true for both of the values of x. So quite a nice example now of how you could do that particular question. Another one we might have now, for example, let's say we've got, let's just do one more to finish with. Let's say we've got 4 to the power now, let's say 2x plus 2. And this one is going to be equal to 8 now to the power of 3x minus 2. Okay, we could write these now as powers of 4 or powers of 8. I personally think it's easier to write them as powers of 2. So what we've got is 2 squared, that's the 4, raised to the power of 2x plus 2. And then we've got 8. Now 8 is 2 to the power of 3, and we'll raise this now to the power of 3x minus 2. So let's go ahead and look at our rules of indices. We're now coming to the third one just here. So now that I've got essentially got the base is the same as 2, all I'm going to do is write now that 4x, so 2 times 2x, 4x plus 4 will be equal to 9x, I'm just multiplying the powers, 9x minus 6. So if I add 6 to both sides and subtract now 4x from both sides, that's going to give me 5x is equal to 10, so x is going to be equal to 2. So let's see if that works and plug those in. So if we think about it at this stage, this is going to give me 4 to the power of 6. And this now, if I sub in the value right here, we're going to have 2, and that's going to give me now, so subbing in 2 here, I've got 2 times 2, which is 4, plus 2, which is 6, and then I've got now 8 to the power of 6 minus 2, which is going to give me 8 to the power of 4. So we can see from this that that is going to work. And if you like, you could write this back just to show that. You could write that now as 2 squared to the power of 6, and that's going to be 2 cubed to the power of 4. So we get 2 to the power of 12. So let's write that there. And that's going to be 2 to the power of 12, which is going to be, what, 4096? A quick guess. I'll let you evaluate that, but 4096 seems a pretty fair punt. So there we go, rules of indices. That's the introduction. In a later video we'll look at some exam style questions. I mean, to some extent these are certainly, these later ones are exam style questions, but it's actually understanding what you're doing rather than being rigid and falling into one particular method as such. So as stated in the next video, we'll have some examples. Some of them will be very similar, some of them will deviate slightly, and I'll show how you can use those certain rules. But hopefully that's been a good introduction so far.